All right. Here we go. By the end of this lesson, you will be able to describe what a Coulomb is and use that to incorporate calculations with Coulomb's law. Okay. If you took notes on the pre-quiz that was due last week, go ahead and pull those out. It'll probably be beneficial for today's discussion.
Oh, no. No. It's disturbing, not disturbing.
All right. For the sake of time, correct answer is D. Dangerous dinosaurs. Okay. This highlights a distinction between chemistry and physics. In chemistry, we looked at individual atoms, and you would count how many electrons there are compared to how many protons there are. You're like 1, 2, 3, 4, 5, 6, 7, 8. This many electrons and this many protons, and therefore the charge is going to be just the difference between the two. Okay. In physics, we're looking at macro-sized objects. Objects that have quadrillions of electrons and protons, trying to quantify the charge, measure the charge based upon just counting electrons and protons. Like, you're gonna be there your whole lifetime, and then, like, this is stupid. We need a better unit. It's like trying to measure from the distance from here to California in inches. That's just ridiculous. We need a bigger unit. We need like miles, okay? And that unit is a Coulomb, okay? A Coulomb, 1 Coulomb of charge is 6.25 times 10 to the 18th extra electrons if it's negatively charged, or extra protons if it's positively charged. So it's a huge quantity. It's like, that's our mile. Okay, 6.25 times 10 to the 18th extra electrons or protons. How are we doing with that? So this is like totally different. Never heard of this stuff before. It's a Coulomb. It's a new unit. It's a huge quantity, extra electrons and protons. Yes. Get a calculator, do process of elimination. Have conversation.
Oh, wait. But it's but a Coulomb it has like 2 more protons, right? But not two more columns, right? A Coulomb has
Okay. If I gave you 2 eggs, how many dozen would that be? 2/12 or a 1/6. Specifically, it would be less than 1. It would be a fraction of a dozen. Okay? A Coulomb is an egg carton that has 6.25 times 10 to the 18th slots in it. If I put I put one proton, two proton, like in this carton, that's huge. That would be a very small fraction of a Coulomb. C. How are we doing? Is that making sense? If you are like thinking A, that was like you're still stuck in chemistry counting. Okay. All right with that? Okay, let's switch to Coulombs. Good? Okay. What I have here. It's an aluminum conductive Coke can, neutrally charged. I'm going to bring a black rod up to it. Tell your neighbor what's going on inside the Coke can.
Is it the same?
Okay, inside the Coke can, which is a conductor. What's going on? Polarizing. Which way are the electrons going? Way. Leaving behind the protons. Some might be tempted to say, oh, well, that should repel because the electrons are going away. Well, we just saw that the Coke can was attracted, even though the electrons are going away. Which one's closer, the exposed protons or the fleeing electrons to the negatively charged rod? Protons. There's a smaller distance between the negatively charged rod and the positive protons. Therefore, the force of attraction is greater because the distance is smaller than the repelling electrons, because there's a greater distance between those. So the overall effect, the net force, is attraction. Does that make sense? There is repulsion going on, but there's a greater force of attraction, therefore attraction wins, and the Coke can is drawn near to the rod. Good? Neighbor? Thank you. Correct answer is D, dangerous dinosaurs.
We're dead dinosaurs. They're
Yeah.
already dead.
D. Good.
Interesting.
Your neighbor.
C.
Correct answer is
C.
C. Why? Newton's third law. For every action, there is an equal and opposite reaction. Good? Tell your neighbor.
So B. Yes.
Are C and D the same thing?
They're not.
What's the difference?
The difference is there's a greater force of repulsion on this guy compared to this guy. And E, there's a greater force of repulsion on this guy compared to that guy.
Oh, yeah, actually, no point. Yeah, I think it's say it's B.
Correct answer is
D.
D.
correct answer is D. Okay? But that guy has more charge. But that guy's got more mass. Okay. Okay. If we would add more charge on this, that's gonna make the force of repulsion greater on both of them. They will always experience the same amount of force because of Newton's third law. Good? Tell your neighbor.
Oh, I think it's.
I was gonna say. So it's always the first one, like the last one just did.
Okay, correct answer is.
C.
So we know that they have the same type of charge, same sign of charge, but the amount, we don't know. They could be the same.
So C.
Correct answer is C.
That's the first time I've ever seen that use that.
Okay, so I've got two spheres, A and B. I want to know I want to try to calculate the electric force between those. What quantities, what characteristics, what measurements should I glean, should I use to figure out the electric force between the two? Mentally select the information that you need. K is constant. Q, charge. Q2, charge. D is distance of separation between their centers. Those three things. Okay. Peanut has a charge of -3 microcoulombs, and the clear strip has a charge of +15 microcoulombs, and they're 30 centimeters apart. How much electric force is acting on them, and which way is the force acting on peanut? Okay, so electric force, K, Q1, Q2 over D squared. Electric force, K, this is 8.99 times 10 to the 9th. That's an always. It's just a constant. Q1, it doesn't matter which one you want to use. I'll use the peanut. So this is going to be 3. So we're going to drop positive and negative signs on the charge. So I'm not going to incorporate negative. Okay, I'm dropping that.
Charge
Okay.
types don't matter.
Now, if I gave you 3 micrometers, you need to convert that to meters, yes? Okay, that would be equal to 3 times 10 to the -6 meters, because that's how you convert micro to anything. Okay, so likewise, I've got microcoulombs. I need to convert that to coulombs. So I say 3 times 10 to the -6 coulombs. That converts that, okay? And 15 microcoulombs, this is 15 times 10 to the -6 coulombs. I know that's improper scientific notation, just roll with it, it works great. And they're 30 centimeters apart, so 0.3 meters, converting that to meters squared. When I plug that in my calculator, I get 4.495. What's the unit on that? What did I just calculate? Force. Electric force. What is the unit of force? Newtons, just like always. Okay? Now, what's going on between the strip and the peanut? How is it forced? Traction or repulsion? How do we know it's attracted? This is where the signs come in. You look at the story. Like, oh, they're oppositely charged. They're attracting. So the strip is being attracted to the right, 4.49 newtons. The peanut is being attracted to the left, 4.495 newtons. So you could say this many of attraction. Okay? Based on opposite charges. Attract. You don't need to write the stuff in the parentheses here. I'm just doing that to teach you. Okay, that's where the signs come in. Okay, so which way is the peanut being forced? To the left. Good with that? So you got a worksheet that's due on Friday. You know how to do it all except for the parts where you have more than 2 objects. If you have 3 objects or more, we'll pick that up tomorrow.